So let's get started on 8.4, mathematical induction. So here's the idea. Is 2 to the n greater than n for all n equal to 1, 2, 3, etc.? And remember, some of our notation we used to use, or we use, is the upside down A means for all n, and that's element of the naturals. Those are natural numbers. So, is it true? So this technique of a proof allows us to prove something like that. So you can first start, if you're trying to actually see if that's true, you'd start plugging in numbers, plugging in 1. Is that true? So yeah, that's true. And then maybe you do another one just to confirm to yourself that that's going to work. So 2 to the 4th is 4. Is that greater than 2? And that is true. Okay, and then 2 cubed maybe. Is that greater than 3? And that's equal to 9. And so yeah, it's looking like it's true. So does that, it's in itself, show it's true for all natural numbers? And of course, your intuition is no. Okay, so basically you're thinking, yep, it seems true. But we don't know it's true for all values. So to prove something like that, so to prove this, we can use what's called the principle of mathematical induction. And it's basically like a format of a proof we will be using to show something like that is true. So here's the outline, kind of what you do. So we're going to say let P sub n be the statement. So be the statement for n. And then we're going to say let K be an arbitrary positive integer. So it's like saying K is in the naturals, but we're not saying it's all of them. It's just some value in the naturals. Then the statement's this, basically. P sub n is true for all n in the naturals if two things happen. 1, P sub 1 is true, which we showed up here. This would be like P sub 1 would be like this, because it's a true statement. You substitute in 1, get a true statement, you're good. All right, so that's the first thing you do. And 2, this is the more difficult part, the truth of P sub k, right? That's for some k, not all of them, but for some k. The truth of P sub k implies the truth of P sub k plus 1, like the next term. Like the next term or next k. So we need to establish that P sub k implies P sub k plus 1. And that's done with legal math moves to get from here to here is what we do. We like multiply on both sides. We do some sort of way to get from one side to the other. All right, so let's look at this example of the one we just did, or just looked at, and we'll see the steps in the proof. So prove by, and it's PMI, principal mathematical induction, 2 to the n is greater than n for all n in the naturals. Then you say proof, and then you say let P sub n be that statement. So we say let P sub n, you got to say it just like this, or very similar, be the statement. 2 to the n is greater than n for all n in the naturals. So it's that entire statement. Then we need to show 1 and 2. So the first one is always to substitute in your 1 and then show it's true, which we've already done that. Right? So 1, P sub 1, means n is equal to 1. And we say 2 to the first is greater than 1 is true. And sometimes, maybe off to the side, you want to convince yourself, this one's pretty obvious, but convince yourself that it's true. Like, is it really working? Because that's part of why you're doing this. Okay, then 2, this is what's called the induction hypothesis step. It's the assumption that P sub k is true. So when you do this proof that's an implication like that, we first have to assume the P sub k. So the antecedent. You need to assume this is true, and then show the truth of this implies this. So you have to say, well, let's suppose it's true. That's called the induction hypothesis. You have to say it like that. Make a statement. Assume P sub k is true for some arbitrary one, not all, but for some k in the naturals. Okay, and that's called the induction hypothesis. Okay, that assumption step. All right, so that means we're saying 2 to the k is greater than k. Now some of this stuff you don't have to write. I'm going to change colors here because this is, you would just kind of keep going, but we want to show 2 to the k plus 1 is greater than k plus 1. So you need to get from here to here using legal math moves, right? Stuff that's, logically true, of course. All right, so we start with P sub k. So here's a little outline here. And your P sub k is 2 to the k is greater than k. All right, so then what you can do, now you do some steps to simplify it. What we want to get to is down here, P sub k plus 1. And what you can do to show this when you're working on it is go ahead and write that down. That's 2 to the k plus 1 is greater than k plus 1. So you know that's where you're heading. And once you get to there, you'll be able to conclude, this is important too, therefore, P sub n is true for all n in the naturals. So you have this outline right here. This is your outline that you're going to be using, all of this. The tough part then is to fill in that hole. You got to figure out how to get from here to here by working with this whole thing. So you can actually work with this first and go back. So let's see. So for example, 2 to the k is 2 times 2 to the first. Okay, so we can do that. That gives you an idea of what to do. So how is this compared to this? Well, the left-hand side is an extra 2 right there. So let's multiply both sides by 2. You can do multiply both sides by 2, a positive number. So what you get then is 2 to the k is greater than 2k. Now, I'm going to make this claim that you can say that's greater than or equal to k, or wait, let's do it like this. Let's say that's equal to k plus k, which is greater than or equal to k plus 1. And how come? Since k is greater than or equal to 1 all the time. So if you just stay at 1, then k is going to be greater. So in other words, well, it's because of this statement here. Basically, it's because of this. You can say that k is greater than 1. So this k is greater than this 1. All right. The next step is a logical implication. You can go from here to here because you're just doing basically transitivity of inequality. So you got this side, and this side gives you to this side. And then we've already established the next step, and you're done. That's it. We've made the connection from p sub k, which is this, all the way down to p sub k plus 1, which is this. Therefore, you make your conclusion, p sub n is true for all n. Okay, let's do another one. So next example, prove by principle of mathematical induction. And I'll basically say that. This is a slightly different one. This is a sum. So the sum, so 1 plus 3 plus 5 plus ... plus 2n minus 1 is equal to n squared. And that's true for all n in the naturals. All right, so first, let's go through our steps. So you say proof, and then we say let p sub n be the statement, and then you restate that whole thing. All right, so let's restate it. So be that statement. And then we'll just basically rewrite it, because you can recopy it. I'm going to recopy it. Oops, didn't mean to cut that. Let's try that again. So be that statement, copy, and then paste. So be that statement. Now, I'm not being real careful here. I like to put this in, although technically you really want this to be the statement, and then you just say this because you're going to change it to k and etc. But I'm not going to be too picky about that, so don't worry about that so much. It's kind of hard enough to grasp at this point sometimes, but it's doable because if you work at it enough, it's doable. You got to start seeing that pattern that's emerging of just there's a format that you do, and there's only a few steps in the middle you have to figure out. All right, so step 1, show, and you don't really even have to say this, but I'll do it a few more times. Show p sub 1 is true. All right, so if n is equal to 1. So what you're doing then is you're adding one term of the sequence. Is that equal to 1 squared? And it's basically, yes, that's true. But you may want to like check it out. Like, well, what if you add 1 plus 3, which is 4. So that's 2 terms of the sequence, which is 2 squared. And 1 plus 3 plus 5, 5, 6, 7, 8, 9. That's 3 terms of the sequence, which is 3 squared. So it seems like it's working. Okay, so it looks like that makes sense. Okay, so I don't need this here. Yeah, that's kind of scratch work. All right, show pieces. All right, so then 2 is the induction hypothesis. Assume P sub k is true for some k. And it's not for all k, it's for some k. Like for some arbitrary k. So assume P sub k is true for some k in the naturals. All right, so then you then state your P sub k here. So P sub k is 1 plus 3 plus 5 plus etc. plus 2k minus 1 equal to k squared. All right, so that's where we start. Now you know where you're going. That's the thing, is you put in down here your P sub k plus 1. And in your work, it doesn't have to be perfect, but I'll be able to move it up if I went too far. So we know where we're heading. It's this same statement, but you put in the k plus 1. So it's 2 times, and then you put in k plus 1 minus 1 equal to k plus 1 squared. So that's exactly what we have to show. You have to get from here up, all the way up here. You have to get from that and then do your steps and end up here. So one way to do that is to start working backwards and then you connect them. Because right now it's like, what do you do? Well, that's why you can work backwards. So I'm going to do that. So 1 plus 3 plus 5 plus dot dot dot. And then this is just 2k plus 2 minus 1. This will be k squared plus 2k plus 1. So that gives you your idea of what to do. Because looky here, you have 2k plus 1 on the right-hand side. So that's essentially what you're adding. And here's 2k plus 1, if you were to simplify that. So this is 2k plus 1, and then k squared plus 2k plus 1. And then all this is the same. So basically then, what you're going to do is add what's missing. This gives you your clue of what to do on both sides. And since it's on both sides, that's a legal move. That's a logical math move. So change my, okay, so add 2k plus 1 on both sides. So it's 1 plus 3 plus 5 plus dot 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 plus. Now this is technically still here, and then you're going to add 2k plus 1, which we already know this 2k plus 1 can be written like this. These are equal. All of those are equal right there. So this term is actually one of those dots. What's that dot? So then that's equal to k squared plus 2k plus 1. And basically that's it, because we've just made the connection that this side is the same as this side, and it simplifies to here. And this 2k, in fact, this is actually redundant. This is the next step right there. But I'll just move up that whole thing. So once you've established that, okay, so there may be just one little step in there that I can put in. That is your k plus 1. So once you've made that connection, this is p sub k plus 1. There's your implication. They're all equivalent statements. Now you conclude. Therefore, p sub n is true for all n in the naturals. Okay. I have down here a few more examples that you can try. There's a lot in the book too, but I might post these in the solutions online, or I'll email online on the Canvas, and I'll go through each one of those proofs. Also, I almost forgot, back here, this will be in the notes as well. Here is are the expansions of the ones we left off on for the binomial. There's the binomial expansion. Here's to the 5th. This is how it expands. And then here's to the 4th. This is how it expands. So you can pause that and take a look. Okay, I think we're going to call it there. There's much to do on these problems, but that's the type of questions that you're going to get for the final. Either one or the other. There's also what's they do in the book. This typical type of question are the divisibility by. So we're not going to look at if it's divisible by, like it divides it, like 2 divides this thing. So we're not going to look at those. We're going to leave those out and just focus on these for this class.